My name is Johnny Him, and I'm with Karthick, Shanmugam, Selvaraj. We both are from the Vertica support group. In this presentation, we're going to talk about best practices for optimizing Vertica performance. We'll discuss, explain plans, what they are and what they do, and how they can help you analyze and troubleshoot a query path. We will also discuss about best practices for projection optimization. We'll talk about directed queries, how they can help you get query performance back using optimized plans. My colleague Karthick will discuss about query profile and the different operators to see where the bottleneck is during the query execution. He will also talk about improving query performance through depot pinning policy and addition of subclusters. There are few things that can impact the performance of a query. This can include query plan, resource allocation, resource contention. We will discuss about query plan and explain plans in this presentation. A query plan is a sequence of step-like path that the Vertica cost-based query optimizer uses to execute queries. Vertica can produce different query plans for a given query. For each query plan, the query optimizer evaluates the data to be queried. Number of rows, columns, statistics, such as number of distinct values, distribution of data across nodes. He also evaluates available resources such as CPU and network topology and other environment factors. The query optimizer uses this information to develop several potential plans. It then compares plans and chooses one, generally the plan with the lower cost. How do you see what query plan the optimizer is choosing for the query? That's when the explain plan comes into the picture. The Vertica user runs explain on a query to analyze how the database processes a query and to see a visual representation of the path that Vertica uses to execute the query. The explain statement returns a formatted description of the optimizer's execution plan for the specified statement. You can use this information to analyze and investigate the query. When you do an explain, it does not execute the plan. Few things that you can check here in the explain plan. There are operators. Vertica executes the operators such as join, sort, filter, limit, as designated in a query plan, using a bottom-to-top approach. Cost. The optimizer calculates the cost for each operator using algorithms that estimate resources for CPU, memory, and network. The estimate of usage of resources is based on the statistics. Projection. The optimizer analyzes possible projections combinations that meet the query requirements to determine which projection has the lowest computational cost. Column materialization provides access to columns for executing the operator. Access refers to opening the column file, encoding, and then compressing based on projection column definition. Path ID. The path ID is an integer value that the optimizer assigns to each query operation for a specific transaction. The path ID helps the optimizer identify the operators at every instance. For a query to perform well, there has to be a good query plan. It is important that statistics be up to date so the optimizer can choose the most cost-effective query plan. If you query a table whose statistics are unavailable or out of date, the optimizer might choose a suboptimal query plan. It is important that you run the function analyze statistics or its equivalent analyze histogram. This function lets you update statistics at various scopes, one or more table columns, a table, the whole database, In the following explain plan, you see no statistics for the item table. When you execute a query using this table, you see in the query events system table that the table statistic is not up to date, and it recommends that you run analyze statistic on this table. When should you run analyze statistics? It's usually recommended that you run it after initial load, after changes of the data, 50% or more of the data. When you see in the query and events table that the statistics needs to be collected on the column. Analyze statistic is a catalog and this IO intensive operation. So do not collect statistics more than necessary. Do not run this on the full database. Do not set small value to analyze row count interval configuration parameter. Projection design optimization. How can we improve the query performance? Few things that you can do to optimize a query. Column encoding and compression, joins of the query, how projections are grouped or sorted, data distribution, column encoding. Encoding reduces on disk size of your data, so the amount of I/O required for query is reduced, resulting in fast execution time. Make sure all columns and projections included in the query use the correct data encoding. As a columnar database, Vertica takes advantage of the data patterns by applying encoding. The goal of data encoding is to reduce storage and therefore reduce the I/O needed to load and read the data. In addition to encoding, Vertica applies compression. In Vertica, the compression process transforms data into a compact form using LZO algorithm. Vertica has many encoding types. Some of them are, for instance, auto and RLE. Auto encoding is ideal for sorted many value columns such as primary keys. It is also suitable for general purpose applications for which no other encoding or compression scheme is applicable. Therefore, it serves as the default if no encoding compression is specified. There's also the run-L length encoding, or RLE. And it should be used for low cardinality columns whose run length is large. The Vertica optimizer gives preference to columns with run length encoding, so be sure to use it whenever appropriate. Another important consideration in order to optimize projection is the type of joins. You can improve the performance of join operations by ensuring projections are designed in a way that lets Vertica choose the fastest join between the inner and outer tables without having to perform additional sort and data transfer operation. When processing a join, the Vertica optimizer chooses chooses from two algorithms, merge join and hash join. Merge join. If both inputs are pre-sorted on the join column, the optimizer chooses merge join, which is faster and uses less memory. Hash join. Using the hash join algorithm, Vertica uses a smaller inner join table to build an in-memory hash table on the join column. Hash join has no sort requirement, but it consumes more memory because it has to build a hash table with the values in the inner table. So, and the optimizer will choose hash join when the projections are not sorted on the join columns. Here's an example of a merge join and hash join. So we have two tables here, table F and table D. Each table has two columns, C1 and C2. When we run an explain of this query, basically, the query is just a left join from these two columns, F and D, left join D on column C1. When you run the explain plan, it produces a join hash. It will show the output of a join hash here. To change that so that it uses merge join, we create two new projections. We call it F merge and D merge. And we're gonna order by C2 instead this time. When we run the same explain query on the same query, we can see that it produces a merge join. Another thing to consider is the group by clause in projections. Vertica implements a group by clause with one of these algorithms, group by pipeline or group by hash. Both algorithms return the same results. Performance of both is generally similar for queries that return a small number of distinct groups. You can use explain to determine which algorithm the query optimizer chooses for a given query. The following conditions generally determine which algorithm is chosen. Group by pipeline requires all group by data to be specified in the projections order by clause. Because group by pipeline only needs to retain in memory the current group data, this algorithm generally requires less memory and executes faster than group by hash. Performance improvements are especially notable for queries that aggregate large numbers of distinct groups. Group by hash is used for any query that does not comply with group by pipeline sort order requirements. In this case, Vertica must build a hash table on group by columns before it can start grouping the data. Here's an example of group by pipeline and group by hash. We create two tables, A and B. Each table has two columns, A and B. When we run an explain on the query, select B, count A from A, group by A, you'll see it uses the group by hash algorithm. On this, to improve that, we create two projections, and these projections are going to be ordered by B. When we run the same explain plan on the same query, it uses group by pipeline. Another consideration when creating optimizing projections is data distribution at runtime. Depending on your query, the Vertica optimizer may need to redistribute data at execution time. This process causes excess network traffic and requires more memory to operate. The optimizer can redistribute data in two ways: broadcast and resegmentation. Broadcast sends a complete copy of an intermediate result to all nodes in the cluster. Resegmentation takes an existing projection or intermediate relation and resegments the data to another node. So it's not ideal to redistribute data across the nodes, for instance, because of you have to transfer the data to the different nodes. The send and receive operator is single-threaded. And when you do this, it has to open a network buffers on all nodes. How we can resolve this? As shown in this explain plan, if it contains resegment or broadcast, the projections are not identically segmented. To improve, Query performance when you join multiple tables. Create projections that are identically segmented on the join keys, or replicate the inner table. Identically segmented projections or replicated inner tables allow the joins to occur locally on each node, reduce data movement across the network during query processing. To improve in group by operations, you need to segment the table by the group by clause. Directed queries. This is a feature that has existed since version 7, but not many people are aware of it, and it can provide big benefits to users. What are directed queries? They're basically queries that you use a mapping between SQL query and one of its execution plan. And directed query has two goals. One, in some rare cases of upgrades, the algorithm behind the query optimizers will change and the query will no longer execute or perform efficiently. You can use directed queries that you created before upgrading to recreate the query plans from the earlier version. 2, enable you to create query plans that improve optimizer performance. A directed query pairs two components: input query and an annotator query. An input query is a query that triggers use of this directed query when it is active. Annotated query is a SQL statement with embedded optimizer hints, which instruct the optimizer how to create a query plan for the specified input query. These hints specify important query plan elements such as join order and projection choices, and a few other things. Vertica provides two methods for creating directed queries. One is created directed query optimizers. Directs the query optimizer to generate an annotated SQL from the specified query input query. The annotated query contains hints that the optimizer can use to recreate its current query plan for that input query. The second one, create directed query custom, specifies an annotated query supplied by the user. Vertica associates the annotated query with the input query as specified by the last saved query statement. Directed queries will store plans in a directed queries repository and call these stored plans when a matching query is executed. Example. Here we have we create a directed query optimizer called find Boston cashiers opt. Then we specify the query, which is a simple query to a dimension table using the filters employee city Boston and job title cashier. Once it is created and saved, then you have to activate it by running activate directed query. When you run the explain plan on this query, it will show that it's using the directed queries. It will have hints such as, on this case, verbatim and proj.js. To create custom directed queries, you will save the query itself. You run the query, you run save query and then specify the query. Then immediately after that, you will create the directed query custom. And then you specify the name of it. You provide the query, including the query hints. In this case, we are providing specific projections. We're using the projection query hint proj.js, and then we're specifying the projection to use, which is an unsegmented dimension projection. Here's an example of an annotated query, a more complicated one. We're adding more query hints, such as syntactic join, verbatim. We're adding proj.js. We're adding the different type of joins, and so on. Here's a different type of query hints that you can use on this custom queries. Syntactic join, the strip, the different type of joins, the proj.js, as I mentioned earlier, and a few other ones. My colleague Karthik will proceed with the next presentation.
Thanks, Johnny. My name is Karthik, and I'm a Vertica support engineer. Johnny explained how you can review the explain plan and projection design to optimize the query performance. In case, if you cannot find any issues on the explain plan or projection design, the next step is to profiling the query and check where the time is being spent. Unlike the explain plan, where cost and row counts are estimated, the counters and plan from the profiling data reflect what really happened. So to profile the query, you can use a keyword called profile before any query statement, which will help you to store the information on DC execution engine profiles. This information allows you to consider how much memory and how many threads of each operator are allocated, how data flows through each operator at different points in time during query execution, also whether a query is network bound. Profiling data can help you in providing valuable input into database design consideration, such as how best to segment and sort projection and facilitate better distribution of data processing across the entire cluster. Operators and counters. There are numerous operators and counters in DC execution engine profiles. The most common operators are join, scan, sort, and network-related operators such as network send and network receive. Regardless of the operators, the most useful counters are execution time, memory allocated, and total number of rows produced. Let me show you some use cases on how to review the profiling data. For example, one of our customers was facing performance issue on one of their queries. When we looked into the execution engine profile data, we can see that one node was taking more time when compared to the other nodes. It happened because there was a data skew on one of the participating projections. So we request our customer to resegment the projections by using appropriate columns. This resolved the issue. On another scenario, data was distributed evenly across all the nodes. However, there was issue with I/O throughput. When we used a validation tool called VOPerf, we can see that I/O throughput was very less on one node when compared to the other nodes, which caused the issue. Like this, we were able to identify the issue and rectify it. For example, you can see there are different operators like here, scan, storage union, join, and for each operator, you can see these counter values like how much the execution time and what, how much the memory requested versus allocated and how many number of rows produced. Like this, you can check these information for all the operators in the DC execution engine profiles. Let me show you some sample queries which can help on reviewing the profiling data. In this query, I'm just checking which operator is taking maximum time when compared to the overall query execution. So in this scenario, join operator is taking more time during the overall query execution. And also in the last column, you can see how many number of threads used for each operator. So like this, you can check which operator is taking more time and how many threads are used, for that query execution. In another query, I'm checking how much total memory requested by the join operator, and I'm checking like whether is there any other activities caused this performance issue. So you can see there are bytes spilled during the join operation, probably because of hash join. So like my colleague mentioned, you can try to use merge join instead of hash join. So like this, you can review the profiling data and identify the issue to rectify it. So far, we saw how you can review the explain plan and profiling data, which are applicable for both EON and enterprise clusters. Now, let me show you some EON specific features that can help to optimize the query performance on EON mode databases. First, depot pinning policies. Depot is nothing but cache of data maintained by the nodes to limit reads from communal storage. Retrieval from communal storage often has high latency and potentially limited bandwidth, especially in cloud environments. When processing a query, the node will first check the local cache for the data they need. If the data is locally cached, the nodes use the cache version instead of retrieving data directly from the communal storage. This will reduces the reads from communal storage, which will improve the query performance accordingly. Depot also expedites load operations such as copy by locally caching newly loaded data until it uploads to communal storage. You can control what all the objects can be cached and retained using depot pinning policies. Those objects are least vulnerable to eviction. So pinning policies can be set at different levels of granularity, such as table level, projection level, and partition level. Also, it can be set at subcluster level or at the entire database. Usage guidelines. There are some useful guidelines that we can follow while setting depot pinning policies. Pin only those objects that are most active in DML operations and queries. Try to minimize the pinned data by setting pinning policies at the smallest effective level, like pinning only active partitions on the partition specific pinned policies. Depot warming. Depot warming helps to ensure that newly added node do not negatively impact query performance. There is a parameter called enable depot warming from peers to enable or disable depot warming. When you set this parameter equal to 1, the nodes that's undergoing startup preemptively loads its depot with frequently queried and pinned data. You can enable the depot warming in the background by setting the parameter called background depot warming equal to 1. So Vertica will continue its depot warming in the background once the node becomes active. Depot fetching. You can configure how you want to fetch data from the communal storage using the parameter called depot operations for query. You can set this parameter in 3 different ways. First, when you set this parameter to all, Vertica will fetch data from the communal storage. If necessary, displace existing files by evicting from the depot. When you set this parameter to fetches, Vertica will fetch data from the communal storage only if there is space available on the depot. Otherwise, it will read queried data directly from the communal storage. The third option and final one, when you set this parameter to none, Vertica will not fetch data from the communal storage. It will read queried data directly from the communal storage. This might impact the query performance. Clearing depot data. It is important that you clear depot data whenever you think those objects are needed in the depot. Because depot can be used for load operations, and you need to have enough space for optimize your load operations. So it's always good to frequently check the depot and clear the data whenever you think those are not used in your future queries. The cached data remains available until it is evicted by Vertica to provide more space for new data or fresher data. Depot data can be cleared at different levels of granularity, like partition level, projection level, and table level. And also you can clear depot at the entire database or on the subcluster level. For example, if you use clear data depot, you can clear whole data from the entire database or whole data from the entire subcluster. So you can use this any of these functions based on your requirement. Monitoring the depot using system tables. You can monitor the depot activities using these system tables. For example, depot underscore eviction. You can use this system table to list the objects which got evicted and what is exactly the reason for the evictions. Either it can be using clear depot pinning policy function, or like providing more room space. So it can be any reason. So you can use this table to check what exactly the reason. Depot underscore files. When you can use this table to check what are all the objects are cached in database depot. You can use a system table called depot underscore pin underscore policies. This will show you the list of objects that are pinned on the depot. Like this, you can use these system tables to check the various depot activities to optimize the depot in your database. Monitoring the depot using MC. You can monitor the depot using management console. Also, you can perform all the above mentioned activities like setting depot pinning policy, clearing depot pinning policy using MC. Also, you can monitor the depot activities using MC. There are default charts you can find in the MC, and you can filter based on the number of days, and you can see how much data reads from communal storage and reads from depot kind of stats, and you can see how much pinned data available in the cache and non-pinned data available in the depot. Like that, you can see these charts and you can understand what exactly happening in the background. So this will be helpful for you to optimize your depot storage and clear the depot whenever you think it's not needed anymore. The final topic is improving query throughput using subcluster. You can use connection load balancing policies to spread the connections across all of the subclusters you created to increase query throughput. Once you set these connection load balancing policies, queries can run only on the subcluster that contains the initiator node. Let me show you the steps how you can set this connection load balance policies. First, you need to create network address for each node in the database. Then you can create load balance group for each subcluster in the database. And you can set routing rule for each load balance group on the database. And there is a function called describe load balance decision, which you can use to see what is exactly happening in the background. So I will show you in the upcoming use case how it will work. So first, in this scenario, I'm having total 6 nodes in the database. So I have created network address for each node in the database. There are total 6 nodes, so I have created 6 network addresses. Next, I have created load balance group for each subcluster. So I'm planning to use default subcluster for ETL jobs and redirecting all other jobs to analytic subcluster. So in this scenario, I created a load subcluster group for default subcluster and analytic subcluster group for analytic subcluster. And you can see, you can set load balance policies. Either you can set it to random, none, or round robin. By default round robin, so I'm in this example, I'm using the policy as round robin. Routing rules. I set routing rules for each load balance group. For example, for first load balance group, I set the IP range, which I'm going to allow for ETL jobs. Next, I don't have any filter set, so all other jobs will be routed to analytic subcluster group. I'll show you what is exactly happening in the background once you set this routing rules. We can use this function, describe load balance decision, to see what is exactly happening in the background. In this example, you can see I passed input IP as 10.20.110.21. Once I executed this function, it will see whether this client IP matches the IP range. In this scenario, it matches the IP range which we set for this routing rule. So 10.20.110.21, which will comes under the range 17 to 30. So input address matches this rule, and all these jobs will be routed to load subcluster group. So all these ETL jobs will be executed on default subcluster. And you can see I'm using a load balance policy as round robin. So it will use round robin algorithm to choose the node from these 3 nodes. So this is the chosen node or IP from these 3 nodes. It used the round robin algorithm to choose the second node. Once it's routed to the load subcluster group, these jobs will be running only within the default subcluster, which contains this initiator node. In this example, I'm passing the IP which is out of range. For example, as per the IP rule, the IP should be within the range 17 to 30. This input IP is out of range. So you can see it says input address does not match the source IP filter for this rule. So it will route all these jobs to analytic subcluster group. And you can see I set the policy as round robin. So it will choose the node based on the round robin algorithm. 10, 30, 34, 85. This is a chosen node or IP based on the round robin algorithm. So all these jobs will be running only on the analytic subcluster, which contains this initiator node. So this is how it will work in the background once you set these routing rules. These are all the reference links which you can use to check these concepts in detail. Let us know if you have any questions. Thank you.